Welcome, everyone. Okay, let's dive into this. Today, we are looking at a concept you've probably encountered years ago, but we're going to completely strip away that old whiteboard anxiety and look at its elegant, profound reality. We're talking about integration. And look, we aren't going to treat it like just some rigid symbol or a boring list of abstract math rules. Instead, we're exploring integration for what it truly is, a practical, everyday language. Specifically, it's the language of accumulation. It's basically the ultimate intellectual tool for figuring out how countless tiny, seemingly insignificant contributions continuously add up to create something incredibly meaningful. Whether it's distance, energy, volume, probability, or even total business revenue mapping across crazy global markets, they can all be understood through this one beautifully elegant idea. It's literally the mathematical translation of how tiny parts become a massive whole.
To really get our heads around this, let's start with a highly tangible puzzle. Imagine you're driving a car. Now, if you're driving at exactly 60 miles per hour for exactly 1 hour, figuring out your total distance is, well, incredibly easy. You went 60 miles. Done. But real life is messy, right? It just doesn't work that way. You stop at red lights, you speed up to pass a truck, you inevitably crawl through endless rush hour traffic. Your speed is changing every single second. So if your rate of speed is constantly fluctuating like that, how on earth can you find the exact total distance you've traveled? You can't just multiply one speed by one chunk of time anymore. You have a rate that literally never stays the same, yet you still need to measure a solid, undeniable reality. This is the exact problem integration was born to solve. And just as a quick aside, if you're into modern video games, this exact logic is running constantly in the background. Physics engines use integration every single frame to calculate exactly where a continuously accelerating object should physically render on your screen. Pretty cool, right?
So the core idea here isn't magic, it is supremely logical. Integration is continuous accumulation. You achieve it by adding very small contributions to recover the total. Think about it philosophically for just a second. Imagine a quantity that's built continuously over time, drops of rain steadily falling into a bucket, tiny slices of physical area forming an entire landscape, or small packets of electrical energy powering a massive city grid. Instead of trying to calculate this overwhelmingly complicated change in quantity all at once, you just slice the problem up. Integration works by isolating tiny fragments, moments in time so incredibly small that your car's speed essentially didn't even have time to change at all, and then systematically adding those tiny contributions up until they form the entire whole.
And this brilliantly illustrates another everyday scenario. Imagine a tank filling with water. If the water flows in perfectly smoothly, great, we can do the basic math. But what if the water pressure keeps changing over time, surging with a huge burst of high pressure, then trickling down to a tiny drip, then surging again? Fluid dynamics in modern engineering constantly battle this exact fluctuating problem. The big question becomes, how much water actually entered that tank after 10 minutes of total chaos? Now, these two questions, the car's total distance on the highway and the tank's water volume, they might look totally different on the surface. One's mechanical motion, the other's fluid volume. But mathematically, there's no difference. They are the exact same puzzle, built entirely on calculating accumulation from a continuously changing rate.
That brings us to the ultimate question integration is always trying to answer. How much has accumulated in total? See, a rate is just telling you how fast something is happening at one specific, isolated moment. That number on your car's speedometer just tells you how fast you're moving right now. But integration zooms out. It grabs all those thousands of continuous right nows and asks for the full story. It kind of acts like a cosmic accountant, collecting all the varying rates, organizing them, and handing you a definitive, undeniable how much. It shifts our entire perspective from instantaneous, fleeting snapshots to the grand narrative of accumulation.
So how do we actually think about this visually? Well, we use a highly reliable three-step mental model. First, we divide the situation into very small pieces. We just split a complex region into thin, easily understandable strips. Second, we estimate the contribution of each individual piece. Basically, we calculate the area of each strip. And third, we simply add all of those strip areas together. That's it. Divide, estimate, add. It's the fundamental act of constructing a whole out of microscopic parts. You're taking a complex, curved, chaotic reality, breaking it down into tiny, predictable rectangles, figuring out the value of each one, and summing them up. In fact, this algorithmic thinking is exactly how modern supercomputers process immensely complex calculus problems today through what we call numerical integration.
Now, what's really interesting about this slide is how perfectly a physical reality maps directly to a mathematical graph. On the left, imagine an irregular physical solid, a strange, organic, bumpy shape. How would you find its volume? Well, you could imagine slicing it into extremely thin slices, kind of like a massive stack of perfectly cut potato chips. If you add up the individual volume of those physical, textured slices, the total volume of the entire object naturally emerges. On the right, we're doing the exact same thing, but to a graph. We take a sweeping, continuous curve and slice the area underneath it into tiny vertical mathematical strips. So you have thin physical slices building a tangible object, right next to thin mathematical strips approximating a conceptual area. It is the exact same foundational logic, just applied in two totally different dimensions.
But of course, if you closely examine those mathematical strips, they look a bit chunky, right? They don't perfectly match the smooth curve. Their rigid little corners stick out a bit over the edges. And that is where the real magic of calculus kicks in. As we move along, we slice the area into thinner and thinner and thinner strips. And as the pieces become smaller and smaller, the approximation steadily improves. This right here is where human imagination meets rigorous logic. By taking this concept to the absolute extreme, literally by making those strips infinitely thin, your approximation stops being a guess. The errors vanish completely. It formally approaches the exact, perfect, completely unarguable mathematical result.
This incredibly elegant process leads us to one of the most practically useful meanings of a definite integral, the area under a curve. This is just a brilliant geometric picture of accumulation. If a graph shows a quantity that changes over time, let's say the curve represents the changing speed of your car, or fluctuating electrical power in a smart grid, or the changing flow rate of a massive river, the integral between point A and point B beautifully measures the total signed area between that curve and the horizontal axis. And I say signed because area dipping below the axis can represent negative accumulation, which would be like your car driving in reverse. Ultimately, the area under that graph is literally collecting those tiny contributions moment by moment. It is mathematically converting a constantly changing rate into a concrete total.
Let's ground this real quick with a comforting, simple mental model, just to prove this doesn't have to be intimidating. You don't always need complex, multivariable equations to do an integral. If your rate is increasing steadily, say the function is just a straight diagonal line, fx equals x, and you look at it from 0 to 3 on a graph, what geometric shape does that actually make? It just makes a simple right triangle with a base of 3 and a height of 3. So what's the total accumulation? It's just the area of that triangle. Base times height divided by 2 gives you 4.5. Boom! Suddenly basic middle school geometry is doing all the heavy lifting of complex accumulation for us. It's a fantastic foundational tool to grasp before tackling those wild, unpredictable curves.
Let's move to and see how this builds into the broader world of calculus. Calculus essentially rests upon two massive main pillars, differentiation and integration, and they are two complementary, intimately linked ways to describe change. Differentiation is asking, how fast is something changing right now? It's finding the instantaneous slope, zooming way in to find the precise rate of change at one incredibly microscopic instant. But integration zooms out to look at the big picture. It asks, what total amount has accumulated over the course of the entire journey?
So the crucial point is that these two operations are literally two sides of the exact same mathematical coin. In many dynamic systems, each operation can completely and perfectly undo the other one. If you know the total accumulated history of a system, you can extract its instantaneous rate of change at any exact point. And vice versa, if you only have a record of its instantaneous rate of change, you can completely rebuild its total accumulation. They are mathematical opposites, continuously looping back into one another in perfect harmony. And this profound, incredibly beautiful connection, this is the fundamental theorem of calculus. It was a monumental breakthrough in human history, and it forms the bedrock that shows exactly why integration can reliably reverse differentiation.
And let me tell you, the real-world power of this theorem is absolutely staggering when you stop to look around. It pops up everywhere a total is being built from continuously changing pieces. In medicine, doctors don't just guess. They integrate a fluctuating dosage rate over time to ensure a patient's total drug exposure is perfectly safe, analyzing how a drug metabolizes hour by hour. In environmental science, experts take a constantly changing pollutant concentration and a varying river flow rate to calculate the exact total toxic load hitting a vulnerable ecosystem over a given month. In technology, integrating your highly variable data transfer rate, which spikes and drops depending on network traffic, tells your internet provider the exact total amount of gigabytes you've downloaded. And in everyday life, everything from analyzing your car's total aerodynamic fuel use, to projecting total rainfall, to calculating your monthly electric power bill is handled by turning a constantly changing rate into a firm total through integration.
Which brings us to our final thought. The next time you see that tall, elegantly stretched out integral symbol on a page or a screen, I really want you to completely change how you view it. Please don't think of it as some mysterious, intimidating mathematical formula meant only for engineers. I want you to think of it as a powerful, probing question. That symbol is actively asking you, what total quantity is being built from all these tiny pieces? Once you start seeing the world through the lens of that specific question, you realize that accumulation is quite literally everywhere. So the next time you look at the constantly changing world around you, ask yourself, what unseen total is currently being built piece by tiny piece?